Hello! We're going to do a continuation of U-substitution. So let me write up, this will be the asynchronous activity. So let me go to writing mode. Okay, so let's just remind ourselves, what is U-substitution? Well, let's say that you're integrating from A to B, and basically it's the reverse of the chain rule. So you're going to have to identify some f prime of g of x times g prime x dx. And then the idea here is that you're doing a u substitution. You're going to identify the g of x in that case, and then you're going to take the derivative of u with respect to x, which will give you g prime of x. And then let's change that a little. We're going to multiply both sides by the differential, so we'll get du equals g prime of x dx. So wherever I see a g of x will now be replaced with a u. And wherever I have g prime of x dx, that will be replaced with du. So this definite integral will now be a definite integral where I have f prime of u. Remember, the u is going to be, the g of x gets replaced with u, and my g prime x dx gets replaced with du. Okay, so that's easier to look at. But the issue here is the bounds. So the bounds a and b, that's only applicable for when my variable of integration is x. My variable of integration here is going to be with respect to u. So you need to change that. You need to find your new values by taking the old values and plugging them into g of x, because u is determined by g of x. Okay, so this is going to be g of a, and this one will be g of b. So let's call those values something. So let's say that we're going to call g of little a, let's call it big A, and g of little b, let's call it big B. So now we'll be integrating from big A to big B. Now we know that if we're integrating f prime of u du, the antiderivative of that is going to be f. So what this becomes is f of b minus f of big B minus f of big A. Okay, so we're going to be doing some examples about this. Let's do our first example. So for this example, we're going to be integrating from 0 to 1 x times e to the 4x squared plus 3 dx. So remember when we talked about this last time, usually you're gonna try to identify your u. Which is the g of x. And then you're going to have your du, which equals g prime x dx. So you're looking for two things that are derivatives of each other, or two things. One is the derivative of the other, right? Because you have your g of x, and you're looking for a matching g prime of x. So if you look, we have this 4x squared plus 3 right here. If you take the derivative of 4x squared, you're going to get 8x, which is, you can make match with this. So what I'm going to do here is I'm going to set my u equal to 4x squared plus 3, which means that my du dx is going to be equal to 8x. So let's start making some changes. So I have my e to the 4x squared plus 3, so that now becomes simply e to the u. Now I have some leftover stuff, the x times dx, and then We're just going to write a and b here because those are going to need to be changed later. We'll deal with that later. So I have x dx here. If I come back to my du dx over here, if I multiply both sides by dx, I get du equals 8x dx. Now I have x dx. These two match, but I have this extra 8, so I'll divide both sides by 8. So I get 1/8 du is equal to x dx. These now match, so I can now replace that whole thing with 1/8 du. So this becomes integral e to the u 1/8 du, and let's actually just move the 1/8 right now outside of the integral using the constant multiple rule. So let's erase this 1/8, just have du there. Okay, now we need to change the bounds. So we need to plug 0 and 1 into my g of x, which is this. So if you plug 0 into that, you get 4, 0 squared plus 3, which is just 3. So this number down here is 3. If you plug 1 into it, you get 4 times 1 squared plus 3, which is 7. Okay, cool. Okay, so let's continue this in green. We're going to get 1/8 of. Okay, now I need the antiderivative of this stuff. So if I take the antiderivative of e to the u, the antiderivative of that is simply e to the u. So I'll get e to the u. So I'm going to be substituting these values, the 7 and 3, into there. So we'll get e to the 7th minus e to the 3rd. So you would just calculate that 1/8 of e to the 7th minus e to the 3rd is approximately equal to 134.568 ... The original integral that we were trying to solve. Okay, let's do one more example. So let's say we're integrating from 0 to pi over 2 cosine squared theta d theta. So we know the antiderivative of cosine. The antiderivative of cosine squared, not so much. So to do this, we're going to first start off by using a trig identity. So you might remember the power reduction rule, which says that cosine squared theta is equal to 1 plus cosine 2 theta over 2. So let's make that change. That we can do with, it's not a change of variables, it's just using a trig identity. So integral 0 to pi over 2 of, and then we get 1 plus cosine 2 theta all over 2 d theta. Okay. And let's change this up a little more. Let's rewrite the fraction. Oops. Let's make that symbol look a little nicer. We'll be integrating from 0 to pi over 2. So we get 1/2 plus cosine 2 theta divided by 2 d theta. So why am I doing this? Well, because it's pretty easy to integrate the 1/2. We'll split this into 2 integrals. I can get an integral from 0 to pi over 2 of 1/2. So I'll factor out the 1/2, and here's my d theta, plus 1/2 integral from 0 to pi over 2 cosine 2 theta d theta. Okay. So let's deal with these separately. We can right away solve the left integral. The antiderivative of d theta is theta. So you'll get 1/2 of pi over 2 minus 0, which will end up being pi over 4. Okay, that's easy enough to do. Now on the right hand side, this is where we can actually start doing a U-substitution. Okay, so looking at this, we can't do anything with the cosine, but we can work with what's in the cosine. So I'm going to take what's in the cosine, which is 2 theta, and that's what I'm going to set up as for my U substitution. So if U equals 2 theta, I can take the derivative of U with respect to theta, and I will get 2. So let's try making the replacement so far. I have cosine. The 2 theta is just U, so I get cosine of U. Now I need to replace the d theta. So we're going to take this equation and we're going to change it a little. I'm going to multiply both sides by d theta, and I get du equals 2d theta. Okay, but I only have the d theta, so I needed to bring the 2 to the other side. So du over 2 equals d theta. So that d theta can be replaced with du. And it's over 2, but I'm going to factor out the 2 in front, and there was already the 1/2 already there. So I'm going to get 1/4. And the bounds are unchanged. We're still going from 0. Oh, no, sorry, I have to change the bounds. So we need to update that. Okay, so I need to plug 0 into this. So let's do that in blue. If you're looking for u of 0, you get 2 times 0, which is still 0. Okay, so you get 0 down here. We also want u of pi over 2. So you get 2 times pi over 2, which is pi. Okay. And now we can integrate. So what's the antiderivative of cosine u? Well, the antiderivative of that is minus sine u. So we're going to have our 1/4, and we will get minus sine of pi minus sine of 0. So sine of pi is 0. Alright. Yeah, and sine of 0 is also 0. So you get 0 minus 0 with times the 1/4, which just goes away. And you're left with the pi over 4 from the original question. I mean, from the left side. Right? Remember, I split it into 2 integrals right here. So you get that this integral equals pi over 4. Because, like as I said, in blue right here, we split up my integral in white up here into the 2. The left one we found was pi over 4. The right one we found out ended up being 0.